I want to share something that confused me for a very long time, and I think it confuses you too. You've probably heard people say, observation changes reality. They say it in a creepy way, like your eyes have special powers, like the moon doesn't exist unless someone is staring at it. And honestly, I used to be confused by that idea as well, because the experiments seem to suggest it. When you don't look, you see an interference pattern. When you do look, the pattern disappears. So what actually changed? Did reality itself change? Or did we just change how the experiment was set up? I want to take you step by step through the biggest mystery in quantum mechanics, the double-slit experiment, and explain what observation really means, why it matters, and why it has nothing to do with magic, even though it's still strange in a deep and beautiful way. When I was teaching quantum mechanics, I kept running into the same trap. Not just students, physicists, smart people. They hear measurement and immediately imagine a person a conscious observer, a mind a moment of awareness. But quantum mechanics doesn't care about your awareness. It doesn't care if you're a poet, a professor, or a frog. It only cares about what happens physically. What interacts with what? The reason this gets tangled is that the word observe in everyday language sounds passive, like looking at something without touching it. But in physics, especially on the atomic scale, there is no such thing as looking without touching. If you get information, you paid for it somehow. The cleanest place to see the whole mess is the double-slit experiment. I loved it because it's brutally simple: two holes, a source, a screen. And yet it contains the heart of the quantum. It's impossible to explain it in any classical way, and it has in it the only real mystery. The trouble is not that it's complicated. The trouble is that it refuses to let you keep your old habits of thinking. So I like to start with comparisons, because your intuition isn't useless. It's just trained on the wrong scale. First, imagine bullets. Ordinary bullets. You fire them at a plate with two holes. Behind it is a backstop where you record where they land. You do it with the left hole open and you get a distribution. You do it with the right hole open and you get another distribution. Then you open both holes, and what happens is perfectly sane. The probabilities add. With both holes open, you simply get the sum of what you would have gotten from each hole alone. That's what a particle does. Now imagine water waves. Same geometry, but waves. Each hole becomes a new source of waves. The waves overlap and you get bright and dark bands, places where they reinforce, places where they cancel. And now you don't get a simple sum. The intensities don't add, you get interference. That's what a wave does. So far, that's classical physics. Particles add, waves interfere. Now I say do it with electrons. And here's the first punch in the stomach. If you detect electrons one by one, you don't get half an electron. You get cliques, identical lumps. No half cliques. But if you run the experiment long enough, those individual lumps build up into a pattern on the screen. And the pattern is not the particle, like some. It's the wavy interference pattern. The electron arrives like a particle, but the probability spreads like a wave. Right there, people start saying the dangerous sentence. It must be consciousness. It must be the observer. No, that's poetry pretending to be physics. What I do when I don't trust my intuition is I try to trap nature with a cleaner question. Not, is it a wave? Not, is it a particle? But, can I find out which hole it went through? Because if I can find out which hole it went through, then it must have gone through one hole, and then the probabilities should add like bullets. So we add a light between the holes so that as the electron passes, it can scatter light, and we can see a flash near one hole or the other. And what happens is perfectly consistent and perfectly upsetting. Every time you get a click, you see a flash near one hole or near the other, never both. So it looks as if the electron chose a definite path. But now the interference pattern disappears. When you watch which hole, the wavy pattern is gone. And if you turn the light off, the interference returns. So did your act of looking change reality? Or did your apparatus change the experiment? This is exactly where the confusion comes from. Now you'll be tempted to say what everybody says, fine, just look more gently. So you say, don't blast the electron with harsh light. Use dim light. Make the observation gentle so you don't disturb anything. I tried that idea in the logic of the experiment, and what we find is something both beautiful and irritating. When you dim the light, the flashes don't become half as bright. They stay full flashes. You just get fewer of them. Sometimes an electron passes and you see no flash at all. That's because light itself is not a continuous fluid. It comes in lumps we call photons. You don't get half a photon, scattering gently. Either a photon interacts or it doesn't. So now we can sort electrons into groups, those for which we saw a flash at slit 1, those for which we saw a flash at slit 2, and those for which we saw no flash at all. And then nature is ruthless. The electrons you saw, the ones for which there is which path information, behave like particles with no interference. The electrons you didn't see, no record of which slit, still build the interference pattern. That's the first big clue. The question isn't, did a human look? The question is, does the world contain information anywhere that distinguishes the alternatives? At this point, you might have the next clever idea, and it's a good one, fine, so dim light doesn't help. Let's make the photon kicks smaller by using longer wavelength light. Because the momentum carried by a photon depends on its wavelength, and longer wavelength means smaller momentum transfer. That sounds like the perfect trick. Learn which path while disturbing the electron less. And then you run into the next wall. If you use longer wavelength light, you lose resolution. Once the wavelength is longer than the slit separation, you can no longer tell which hole the electron went through. The flash becomes a big blur, and exactly in that regime, the regime where you cannot know which path, the interference returns. When you can know, it vanishes. When you cannot know even in principle, it comes back. It's as if nature is saying, you may have which path information, or you may have interference, but you don't get to have both in the same run. Now people ask me, so does observation change reality or not? And I have to slow them down because the question is sloppy. It mixes two different ideas. One idea is, are we merely learning something about a reality that already has definite properties? The other is, are we creating those properties by measuring? The double slit pushes you toward a sharper statement. You are not allowed to insist on a classical story when the experiment doesn't support one. Here's the rule that keeps you from making wrong predictions. If you have apparatus capable of determining which hole the electron passes through, then you can say it went through one or the other, because the experiment has arranged for that statement to have a definite meaning. But if you do not try, if nothing in the experiment distinguishes the alternatives, then you may not say, went through one or the other, and then use that statement to compute outcomes, because it will make you compute the wrong thing. That's not philosophy, it's bookkeeping. It's a rule for staying consistent with experiments. This is where the internet goes crazy and says, "The electron knows you're watching." No. The electron doesn't have a little homunculus inside, peeking out. What happens is that to gain which path information, you must couple the electron to something else. Light, a detector, a field, a mark, so that the electron's alternatives become correlated with distinct states of something in the world. In modern language, you might call it entanglement. In plain language, you can say, the alternatives are no longer able to interfere because the world now carries a record that distinguishes them. And you can see why it's not consciousness with a simple thought, replace your eyes with a photographic plate. Store the data on tape. Don't let anybody look at it for 100 years. If the information exists in principle, the interference is still gone. The universe doesn't wait for you to feel enlightened. It evolves. At this point, there's a deeper question that bothered me for a long time, because it's where the simple slogans break. Where exactly is the boundary? When does a mere interaction become a measurement? Is it a photon, a molecule of air, a Geiger counter, a human brain? If you say collapse happens only when a conscious observer looks, you've put minds into physics as a special ingredient, and then you're obligated to define what a mind is, and that's no way to run a universe. Physics should not depend on whether a cat is conscious. So I asked myself, if it's not consciousness, what is it? What actually changes in the mathematics and the physical situation when we observe? Here's how I like to picture it. Think of each alternative history of the electron through slit 1 or slit 2 as a story the universe could tell, and each story has an amplitude with a phase. When nothing marks the path, the two stories remain compatible and the amplitudes add. That's interference. But when you add a witch path detector, you don't merely learn the story. You force the electron's history to become correlated with distinct states of the detector. Now, instead of electron through 1 plus electron through 2, you have electron through 1 and detector says 1, plus electron through 2 and detector says 2. Those detector states are different physical states. They don't overlap. They don't interfere. And if you don't keep track of the delicate phase relationships between those huge detector states, then for the electron alone you end up adding probabilities. That's why measurement feels irreversible. Not because the laws suddenly change, but because the information has spread into the environment in a way you cannot practically unscramble. So the boundary is not a spiritual boundary. It's a practical boundary of coherence. How hard is it to keep track of phase relationships between countless degrees of freedom? For macroscopic objects, it's essentially impossible. The interference is gone. Now I want to be careful. I'm not claiming every philosophical interpretation is settled. Physicists still argue about meaning. But the confusion we started with becomes much clearer. Observation changes the experimental situation by coupling the system to the apparatus and the environment. That changes what kinds of patterns can appear. When people say reality changes, they often mean the pattern on the screen changes. That's true. But it doesn't require a mind. It requires interaction and information. Here's the turning point for me: the word observation is misleading because it suggests something passive. But in quantum mechanics, observation means the world has been forced into a situation where certain alternatives can no longer interfere. Interference is not a property of an electron alone. It's a property of an entire arrangement. Change the arrangement, and you change what behaviors are possible. If the alternatives are indistinguishable, you must add amplitudes and you see interference. If the alternatives are distinguishable, you add probabilities and the interference disappears. And you don't get to ask both questions at once. And then it hit me, the phrase, observation changes reality, is half true. But for a reason much more ordinary than people think and much more profound than they realize. It's ordinary because to observe is to interact, and on the atomic scale you cannot interact gently enough to keep everything the same while also extracting which path information. It's profound because the thing that changes is not what the electron really did in secret, as if it had a classical trajectory all along. The thing that changes is whether the alternatives can combine as amplitudes or must separate as probabilities once a record exists in the world. So I can say it precisely, without mysticism, observation does not require consciousness. Observation is any physical process that creates distinguishable outcomes, any process that correlates the system with the rest of the world so that the alternatives are no longer able to interfere in the way they did before. When that clicked for me, the spooky mind magic evaporated. The real mystery remained, but it was a clean mystery, not a sloppy one. And the remaining mystery is still there. Why does nature run on amplitudes at all? Why is the rule that probabilities come from squaring amplitudes the rule? Why does interference disappear when alternatives become distinguishable? We can describe it, compute it, and build technology with it. But if you demand a classical mechanism underneath, little billiard balls with hidden plans, you run into trouble. This changed how I see reality, not because it made the world subjective, but because it made me respect the difference between what I can say and what I can merely imagine. In everyday life, imagination is cheap. In quantum mechanics, imagination can trap you if you start insisting on statements that have no experimental meaning. The lesson I keep coming back to is simple. Don't fool yourself. When your intuition says the electron must have gone through slit 1 or slit 2, even if you didn't look, you have to ask whether that statement helps you predict anything or whether it makes you predict the wrong thing. So does observation change reality? It changes what can happen next because observation is a physical interaction that changes the whole situation. But it doesn't mean you think the electron into existence. It means you join the experiment. And I hope you can see what I see, not a universe that waits for you to look, but a universe so delicately consistent that the mere possibility of information decides whether histories interfere. That's the beauty of quantum mechanics, and I wanted you to experience it with me.